In this lab, we'll take a look at quantum systems. In these systems, the total energy takes on discrete values that we describe with energy levels. Each level can be labeled with a quantum number n. Since the energy comes in discrete values, changes in energy are also discrete and correspond to changes in energy level. This means that the energy emitted or absorbed by the quantum system has to match up with energy differences between two levels. This means that photons emitted or absorbed by the system can only have certain wavelengths. We'll look specifically at the hydrogen atom, where the wavelengths of emitted light are described by the Rydberg equation. We'll see that transitions to the final level of n equals 2 correspond to emitted wavelengths in the visible spectrum of light. So in this lab, we'll measure the wavelengths of light emitted by the excited hydrogen and verify that these wavelengths are predicted by the Rydberg equation. To measure the emitted wavelengths, we'll use a spectrometer, which is a tool to precisely measure diffraction angles from a grating. Recall that the angle of diffraction increases with wavelength, as described by the equation d sine theta equals m lambda. Let's take a look at the spectrometer. On the input side is a collimating tube, which has an adjustable aperture so you can control the amount of light that gets through. The light that does get through the tube is collimated before it hits the diffraction grating. The grating is mounted perpendicular to the incoming light. Light diffracts from the grating and can be viewed again by a telescope. The angle between the telescope and the collimating tube is indicated on the platform of the spectrometer. Before we trust these angle measurements, we'll have to calibrate the spectrometer.
So to calibrate the spectrometer, you'll need to use the mercury source, which has one brightest wavelength, so it's easy to use as a calibration. So here's the 0th order, and as I rotate around, you can see there's the 1st order. There's two different lines, but one's bright green, and you'll be able to see that one much more sharply. The other's a little bit more of a yellow color. So this is the 1st order diffracted beam for both of those. And then as you keep going, you'll see the 2nd order. And you can see kind of to the left a little bit the yellow. And so they're separated by a little bit more. So you get higher resolution as you go out to higher orders. Then as you keep going, you can start to see the 3rd order come in. There it is. And so this is what you'll be doing, but you'll be making more accurate measurements. So to use this, you push the spectrometer directly up to the source. So all the light from the hydrogen source gets through the input of the spectrometer. And now if you look through the grating, you can see that there's the source. But we don't want to look directly at it. What we want to do is look through this telescope at it so that we can see the diffraction angles. So if I move this here and we try and look through the source, or look through the telescope, then we can see that there.
You'll adjust the telescope angle so that the crosshairs are in the center of the band, and then measure the angle. As you increase the angle of the telescope, you'll see colored bands of diffracted light corresponding to the different hydrogen transitions.